Hi friends, welcome to somethingcalledscience.com. Today we'll talk about the fascinating topic of thermodynamics for class 11. Imagine you're holding a hot cup of coffee on a cold morning. After a while the coffee cools down and the cup feels less warm. Ever wondered why this happens? This is thermodynamics in action. Energy in the form of heat is transferring from the hot coffee to the cooler surroundings. Thermodynamics is the study of energy, heat, and how they move and change during any physical and chemical process, like ice melting, wood burning, or water boiling. In thermodynamics, we divide the universe into two parts. The system, which refers to the specific part we're interested in studying, like the chemicals in a beaker during a reaction, and the surroundings, which refer to everything else around the system, the beaker, the air, the table, or the room. What's important is that system and surroundings can exchange energy and sometimes matter. Systems can be classified based on how they interact with their surroundings. In open systems, both energy and matter can freely move between the system and surroundings, like with a boiling pot without a lid. In closed systems, only energy can be exchanged, but matter stays locked inside, like with a sealed water bottle that you heat up. Isolated systems are the most restricted type. Neither energy nor matter can get in or out, like with a perfect thermos flask. Now that we've looked at the basics of systems, let's explore the fundamental laws that govern how energy behaves. We'll start with the first law of thermodynamics. Here's the big idea. Energy can neither be created nor destroyed. It can only be converted from one form to another. This is also called the law of conservation of energy. When you burn wood, the chemical energy in the wood doesn't disappear. It transforms into heat and light energy. The total amount of energy remains the same. In chemistry, we express this as delta U equals Q minus W. Delta U is the change in internal energy of the system. Q is the heat absorbed or released, and W is the work done by or on the system. This simply means that the change in a system's energy equals the heat it exchanges minus any work done by the system. So if a system absorbs heat, its internal energy increases. If it does work, its energy decreases by that amount. Let's break down what heat and work actually mean in this context. Heat, or Q, stands for energy transferred because of a temperature difference. Heat always flows from hot to cold, like warmth from your hands melting an ice cube. Work, or W, stands for energy transferred when a force moves something. In chemistry, this often means a gas expanding or contracting, like when a gas pushes a piston. In thermodynamics, the direction of heat and work is important. By convention, work done by the system on surroundings is positive, and work done on the system is negative. The following sign conventions are used. When the system absorbs heat, Q is positive, and this increases the internal energy delta U. When the system releases heat, Q is negative, which decreases the internal energy. When work is done by the system, such as during expansion, W is positive, and the internal energy decreases. Finally, when work is done on the system, such as during compression, W is negative, and the internal energy increases. Let's look at a simple example to make this clearer. In the meantime, you can find a full transcript of this video and a worksheet on our website. Imagine that a gas absorbs 200 joules of heat and does 50 joules of work, like by expanding in a piston and pushing against the surroundings. This means that work is done by the system. Thus, W is positive. Let's calculate the change in internal energy. Delta U equals Q minus W, which is 200 minus 50 equals plus 150 joules. So the internal energy increases by 150 joules. Even though the system does work, which by itself would decrease internal energy, the heat absorbed is greater than the work done, so the net effect is an increase in internal energy. Now let's talk about a concept that's especially useful for understanding chemical reactions in the lab: enthalpy. Most chemical reactions happen in open containers at constant atmospheric pressure, like in a beaker on your lab bench. For these conditions, we use a special term called enthalpy, or H. At constant pressure, the heat absorbed or released by the system is equal to the change in enthalpy. Delta H equals Q sub P. The change in enthalpy, or delta H, tells us how much heat is absorbed or released during a reaction at constant pressure. There are two types of reactions. In exothermic reactions, heat is released to surroundings, meaning that delta H is negative. These reactions feel hot. Examples are burning wood or the rusting of iron. In endothermic reactions, heat is absorbed from surroundings, meaning that delta H is positive. These reactions feel cold. Examples are melting ice or evaporating water. Now let's look at different types of enthalpy changes that chemists commonly measure. In chemistry, we measure different kinds of enthalpy changes depending on the type of process occurring. These measurements are typically made under standard conditions, meaning 298 K or 25 degrees Celsius and 1 atmosphere pressure, and they are indicated by the symbol for standard. The standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. If it is negative, the formation is exothermic, energy is released. If positive, it's endothermic, energy is absorbed. By convention, the standard enthalpy of formation of any element in its standard state is 0. The standard enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in excess oxygen under standard conditions. Combustion reactions are always exothermic, a negative delta H, which is why burning fuels releases heat. The standard enthalpy of neutralization is the enthalpy change when 1 mole of water is formed from the neutralization of an acid by a base under standard conditions. Finally, the standard enthalpy of solution is the enthalpy change when 1 mole of a substance is dissolved in a large excess of solvent, usually water, so that further dilution produces no additional heat change. Understanding these different types of enthalpy changes is crucial, but how do we calculate enthalpy changes for reactions that are difficult to measure directly? That's where Hess's law comes in. Sometimes we want to know the enthalpy change for a reaction that's difficult or impossible to measure directly in the lab. Hess's law provides a way to calculate this. Hess's law states that the total enthalpy change for a reaction is independent of the route taken. In other words, if a reaction can occur in multiple steps, the total enthalpy change is the sum of the enthalpy changes for each step. This works because enthalpy is a state function. Like internal energy, Q, it depends only on the initial and final states, not on the path taken between them. Think of it like climbing a mountain. Whether you take a direct steep path or a winding gentle path, your change in altitude from bottom to top is the same. Similarly, whether a reaction happens in one step or multiple steps, the total enthalpy change is the same. This is different for heat and work, which are path functions, because they depend on how the process occurs. This distinction is fundamental to understanding thermodynamics. To find the enthalpy change for a target reaction, identify known reactions with known enthalpy changes that can be combined. Manipulate these reactions, reverse them, multiply them as needed, and then add them together. Remember, reversing a reaction changes the sign of delta H, and multiplying a reaction multiplies delta H by that same factor. Let's look at an example. Suppose we want to find the enthalpy change for solid carbon plus half O2 gas gives CO gas, which is hard to measure directly. From known data for carbon to carbon dioxide, delta H1 equals negative 394 kilojoules per mole, and carbon monoxide to carbon dioxide, delta H2 equals negative 283 kilojoules per mole. We can reverse the second equation and add. Carbon solid plus oxygen gas yields carbon dioxide gas. Delta H1 equals negative 394 kilojoules per mole. Carbon dioxide gas yields carbon monoxide gas plus 1/2 oxygen gas. Delta H equals positive 283 kilojoules per mole. Overall, carbon solid plus 1/2 oxygen gas yields carbon monoxide gas. Delta H equals negative 111 kilojoules per mole. This is the power of Hess's law. We can calculate enthalpy changes for reactions we can't easily measure. Now that we understand enthalpy changes, let's talk about how we actually measure the heat absorbed or released in chemical processes. Have you ever noticed that water takes longer to heat up than oil? Or that a metal spoon gets hot much faster than a wooden spoon when placed in hot soup? This is because different substances have different abilities to absorb heat. We call this heat capacity. Heat capacity is the amount of heat required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. There are two main types. Specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Different materials have different specific heat capacities. Some examples are water, which has a high specific heat capacity. It takes a lot of energy to heat up water. And metals like iron, which have lower specific heat capacities. They heat up quickly. Molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a substance by 1 degree Celsius. This is especially useful when dealing with chemical reactions. To calculate the heat absorbed or released when a substance changes temperature, we use Q equals mc delta T. Q is the heat absorbed or released. M is the mass of the substance, C is the specific heat capacity, and delta T is the change in temperature. This equation allows us to calculate how much heat is needed to change the temperature of any substance. Scientists measure heat changes in chemical reactions using a technique called calorimetry. A calorimeter is an insulated container designed to measure heat changes during physical or chemical processes. When a reaction happens inside, any heat released or absorbed changes the temperature of the water in the calorimeter, allowing us to calculate the heat of the reaction. The key principle is conservation of energy. In an insulated calorimeter, the heat released by the reaction equals the heat absorbed by the surroundings, usually water. Negative Q of reaction equals Q of water. Since Q equals mc delta T for the water, we can determine the heat of reaction by measuring the mass of water, its specific heat capacity, and the temperature change. Thermodynamics helps us understand energy changes in chemical reactions. The first law tells us that energy is conserved. It can only be transformed from one form to another. We use concepts like internal energy, heat, work, and enthalpy to describe these energy changes and understand whether reactions release heat, exothermic, or absorb heat, endothermic. The beauty of thermodynamics is that it's a universal set of rules that governs all energy transformations in the universe. A big thank you to our Patreon members. You're all awesome and helping out the channel a lot. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more science content. It really helps the channel out. Let us know in the comments if you have any questions or topics you'd like us to cover next. Thanks for watching and see you in the next video.